Hello, today we're going to take a look at scientific notation, which is just a slick way to write really big numbers or really small numbers in a much more compact way. It's used often in the sciences, as the name suggests, with scientific notation, because in the sciences you're often dealing with huge numbers of molecules, atoms, bacteria, and you want to express that number much more succinctly than having to write a long string such as like 4 trillion as we have in the example A here. You've got Avogadro's constant, which is approximately 6.022 times 10 to the 23rd, which is a really popular thing in sciences and chemistry. So it's used a lot in science, but it relies on mathematical principles, and it relies a lot on exponential rules and notation. So we're going to take a look at it here. I'll do this first example, then we'll try and break down the process step by step. So if I want to express this really large number here in scientific notation, it looks like about 4 trillion, I'm going to put my decimal point here and count how many spaces I'm going to move to the left. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm stopping at that first number. So I then write 4.062 times 10 to the 12th because I moved 12 decimal places over. And that's it in scientific notation. Now what do we do there? Well, first step, move your decimal point to the first number on the left, to the right of the first number. Okay, so I stopped it right before that first number. Next, and this is kind of as you're doing that, count the number of spaces that you moved the decimal point. And that's going to end up being the exponent when you write times 10 to whatever number of spaces you moved. And then thirdly, remove extra zeros and write the number of the form, write the number as, because notice up there, I don't have 4.062 0. I got rid of those, and that's what makes this notation nice. I don't have to write all those zeros. So I'm going to write the number as A times 10 to the nth, where n is the number of spaces I moved, if I move to the left, if I moved left, or I'm going to write it as A times 10 to the negative n if I move to the right, which I'm going to do in our next example. Alright, keep those in mind. Express, looking at B up here, express 0.0000452 in scientific notation. So I'm taking my decimal point, and I'm going to move it to the right of the first number on the left. Got that? To the right of the first number on the left. So I now have 4.52. And how many times did I move? 1, 2, 3, 4, 5. So 4.52 times 10 to the negative 5. And that would be our number in scientific notation. Now notice, this makes sense because what this is saying actually is take my number, 4.52, multiply it by 10 to the negative 5th. Well, 10 to the negative 5th would be a number 1, 2, 3, 4, 0.5 right there. That would be 10 to the negative fifth, and you multiply those together and you would get our number up top there. And this is just a shorthand way of doing that. Now, trying to go the other way with our scientific notation, can I take scientific notation and write it in standard form? 6.49 times 10 to the fifth. A positive exponent, I'm going to move the decimal point 5 spots to the right. So I'm going to have 649. I'm going to go 1, 2, 3, 4, 5. Put my decimal point and fill in with zeros. So I have 649,000. Boom. That would be 6.49 times 10 to the fifth in standard form. The positive exponent here is saying move my decimal point to the right. Express 1.8 times 10 to the negative third in standard form. Okay, the negative here is move to the left. So I'm going to go 1, 2, 3 to the left, put my decimal point, and fill in those extra spaces with zeros. So I get 0.0018. Okay, good. Now I can try, if I were to write this number in scientific notation, I would put my decimal point here, where it should be. How many spaces do I go? 1, 2, 3, 4, 5. So it's 3.048 times 10 to the fifth. Quick example right there, and I just wanted to point out, see, I no longer need these zeros. Those are extra. They're not necessary in my scientific notation. I take away all the zeros behind my last non-zero digit. Let's do some math with scientific notation. Evaluate 8 times 10 to the fifth times 2.1 times 10 to the negative third. Doing these problems, I can multiply the kind of normal looking numbers and then multiply my 10 to the power numbers. And this is where our properties of exponents come into play. Because we remember when we multiply numbers with the same bases, we add the exponents. So first the numbers. 8 times 2.1, that is equal to 16.8. And then you're going to say times 10 to the... Okay, so I'm multiplying same bases, so I add the exponents. 5 plus negative 3, 10 squared. Hold on a second though. Every time you're in scientific notation, just like I did in that last short example, there should be only one number before the decimal point. Here I have 2. So this is not in correct scientific notation. Rather, I need it to be like 1.68 times 10. But now that I moved the decimal place 1 to the left, I need to increase it 1. Because every time we move that decimal point to the left, my scientific notation goes up 1. Move left, exponent up 1. Got it? So we have to make sure our final answer is in correct scientific notation. Last problem here. Evaluate 4.5 times 10 to the 8th divided by 1.5 times 10 to the 10th. So I can divide those numbers. 4.5 divided by 1.5 is a slick and clean number 3. And then times 10 to the 8 divided by 10. Well, same bases. So remember our property, if I'm dividing same bases, I subtract the exponents. So it's times 10 to the negative 2. And we could leave our answer like that. That has a value of, let's practice this. So it's 3 times 10 to the negative 2. So I move left 0.03. So 3 times 10 to the negative 2 is actually 0.03. And these are equivalent answers there. One in standard notation and one in scientific notation.